Hey guys, this is Professor Janacek. I want to do some more examples of looking at the root test to determine convergence of a series. Let's try the sum as k goes from 1 to infinity of 1 over k minus 1 over k squared raised to the k. Again, remember with the root test, we actually take the limit as k goes to infinity of the kth root of the absolute value of the terms of the series. Notice again, I'm not putting an equal sign there. This is not equal to the limit, right? I'm going to evaluate the limit to tell me what's going on with the series. All right, so what can we do here? Well, quite easily. In this case, I have a k as an exponent, k as an index. Those are opposite operations. They will go away in the next step. Let's see. The limit as k goes to infinity, don't forget to write that limit notation every time, of the absolute value of 1 over k minus 1 over k squared. Okay, to take this limit, I think it'd be really nice if we could kind of put all this together. Let me get a common denominator between those two. So we have k minus 1 over k squared. All right, to take this limit, I'm going to use that little technique from Calculus 1 where we look at the highest degree of the denominator. I always want to use this anytime I have a rational expression, a polynomial in the numerator, a polynomial in the denominator. Oftentimes people want to go straight into L'Hopital's rule, but don't need to use that here. So in the denominator, I have k squared, which means I'm going to multiply by 1 over k squared in both the numerator and the denominator. Again, putting that in absolute values is not a problem because k is going to infinity. All right, distribute that in. And we have 1 over k minus 1 over k squared over 1. All right, well, let's see. As k gets really large, 1 over k gets really small. And as k gets really large, 1 over k squared gets really small. Meaning the limit of the numerator, we end up with 0 minus 0 over 1, which is 0, which, by the way, is less than 1. If this limit is less than 1, then we know that our series converges. Not too bad. Let's try another one. How about the sum as k goes from 1 to infinity of k factorial raised to the k in the numerator and 2 to the k raised to the second power in the denominator. Okay, so for the root test, I'm going to take the limit as k goes to infinity of the kth root of the absolute value of the terms All right, a few things we can do. Let's just look at that denominator for a minute. I really want to have that as a k in the exponent without that 2. So let's move things around a bit. That, let's see, 2 raised to the k, then raised to the 2 is 2 to the 2k, right? Power to a power. We multiply those exponents. But now I can kind of undo that multiplication. Multiplication is commutative, if you will. By the way, that should be a k. That gives us 2 squared to the k. All right, well, now that's kind of nice. Kth root, k and an exponent in both the numerator and the denominator. That will simplify. So we get the absolute value of k factorial over 2 squared. And yes, if you want to go ahead and square 2, you're welcome to. Not necessary though. I can see right away what's happening with this limit. Notice k is going to infinity, so k factorial is also getting really, really large, meaning this whole thing goes to infinity. Well, if it goes to infinity, then that means, let me jot all this down again, this whole limit must be greater than 1. And if it's greater than 1, then the series diverges. Enjoy!